Right. So question number 7. An image of the sun is formed by a lens of focal length 30 centimeter or on the metal surface of a photoelectric cell, and it produces small current I. The lens forming the image is replaced by another lens of the same diameter but of focal length 15 centimeter, which is different this time. What will be the photoelectric current in this case? This does seem like a conceptual question. So, what will be the photoelectric
Yeah,
current?
here you are given the focal length of two lenses.
Mm-hmm.
One is given to be 30 centimeter,
Mm-hmm.
the other is 15 centimeter.
Mm-hmm.
So you might get confused with this. We have a lens here, and the sun rays are parallel rays which will come after passing through the lens till coincide at the focus.
Yes.
This is the focus. So for one lens this is 30, for the other this is 15.
The distance between the focus and the
Yeah, the
lens,
lens optical center and the focus.
Right.
So this distance is
Mhm.
for one it is 30, for the other it is 15.
Right.
So you might be confused what to do because you don't have a ready-made formula for this.
Mm-hmm.
What I'm going to tell you is that you do not actually need the focal length.
Mm-hmm.
Here it is just to trick you. This 15 centimeter and this 30 centimeter, basically this is not actually used in the problem.
Oh, isn't it?
Yeah, so what we use is actually this thing, which you might not even notice while looking at the question for the first time.
Right.
The lenses are of the same diameter.
Mm-hmm.
So you know that photoelectric current depends on the intensity of the light rays.
Right.
The light rays, if they're causing photoelectric current in one of the lens, that means the frequency, the threshold frequency of the metal is lesser than the rays that are incident on it. So
Okay.
no matter what radiation falls on it of this frequency, it will cause a photoelectric current. The question is about the intensity.
Right.
So how do you know about the intensity? See, if this is a lens, if we look at it from the top, this is the diameter, and so the area of both the lenses is the same.
True.
So when rays fall on it, number of photons passing through it would be the same for both lenses, since they have same diameter, same area.
And both of them,
So both of
sunlight is
them,
falling them on both.
yeah, sunlight is falling on them, and so both of them will have the same intensity.
Yes.
And all of them, like all of the rays would go and coincide at the focus, whether it be 30 centimeter or 15 centimeter, doesn't really matter. So because all the rays would coincide at that point, so the intensity would remain the same.
Okay.
So intensity is directly proportional to photoelectric current. So if it is I here, it will be I here as well. So the answer would be I.
Oh, okay. So this is a very trick question, isn't it?
Yeah, like they might include other facts as well. Like they might give you mu1 and mu2, which is the refractive index of the lens. They might change the lens as like totally by replacing it with some other, like say liquid lens or something.
Okay.
Doesn't really matter. The net result would be the same because the intensity is the same.
Right. So basically, the main thing which we have to keep in mind is that it's the same diameter, right?
Yeah, so which gives the same intensity.
Right. So these kind of questions also might be asked where they might give you random figures and numbers and values where they might want to confuse you and might want to make you unsure of your own answer.
Yeah, like if they give you numerical values, most of the students, what they do is they go to the numerical values and try to correlate some formula with it. But the same diameter is written in words, so many of us would not even consider that fact. Like we'll just move away from it, and that will cause us our marks.
Right. Brilliant. So question number 7, one very important lesson what we learned was to make sure that we take only inputs from the question which are relevant to the answer. So here the focal length of the lenses weren't actually very relevant inputs as such. So since it was the same diameter, it has the same surface area, and the intensity would be same, and so hence the current produced due to photoelectric effect would be the same. It's not I by 2, it's not 2I, it's not anything like that, it's just I. So the final answer, again as we stressed it out, it is I.
Yeah, for I we have actually sometimes they might put the option like I, 2I, 3I, and one of the option will be none of these.
Right.
Most students would like 2I, 3I, and I by 2. Those would be the answers they would look to.
True.
And since I would not be there, no one would click none of this, and then they'll lose their marks. So these are the things you need to consider.
Right. So brilliant. So this was question number 7, and yeah, we learned that we should take care of how we approach a problem, and you should take care of it to a very great extent. So coming to question number 8, a photon of wavelength 19.8 nanometer collides with an electron at rest. After the collision, the wavelength of the photon is found to be 30 nanometer. Calculate the de Broglie wavelength of the electron. Right, so we entered the concept of de Broglie wavelength. So can you just tell me very briefly as to what de Broglie wavelength is?
Yeah, de Broglie wavelength. The de Broglie equation basically relates the wave nature with the particle nature of different materials like electrons, photons, whatever you consider.
Okay.
All have a wave nature as well as a particle nature.
Right.
That's the basic thing we get from dual nature of radiation and matter.
Right.
So here in de Broglie we get that lambda equals to h by p. P is the momentum. H is the Planck's constant. Lambda is the de Broglie wavelength.
Right.
So P we can replace by mv as well. M is the mass of the particle and v is the velocity.
Yes.
So this is basically the de Broglie relation for like wave particle dual nature.
Okay.
So here to proceed with this problem, first we find out the initial energy of the photon.
Right.
The initial energy let us take as EI, which is h nu I. Nu I is given as this is the wavelength. We'll calculate it using h c by lambda I.
Yes.
And we substitute these values 6.6 into 10 to the power minus 34, which is the value of h, Planck's constant. C is 3 into 10 to the power 8. You need to remember these values as these are constants.
Yes.
Even if they are not given, you have to put the values.
Right.
Then lambda 1 is given as 19.8. This is in nanometers, so multiply with 10 to the power minus 9.
Right.
Like I would like to remind you again, do not forget to put this 10 to the power minus 9 thing, otherwise your whole problem would go in vain. So we come to the initial energy, that is 10 into 10 raised to the power minus 18 joules. This is the initial energy of the photon.
Right.
So next we consider the case after the collision, that is the final energy of the photon.
Okay.
So we take it to be EF. In the same way we calculate it.
EI. Lambda F.
So we substitute the values like that itself, and
lambda F here is 30 nanometer, I believe.
Yeah, it is 30 nanometer. That is after the collision, the wavelength of the photon.
True.
So it comes to be 6.6 into 10 raised to the power minus 18 joules after substituting similarly as in this part.
Right.
So this is the final energy of the photon.
Okay, so now we have the initial energy of the photon before collision and we have the energy of the photon after collision.
Yeah, we have both of this.
So basically the difference of them will give us the kinetic energy.
Yeah, it will give us the kinetic energy of the electron. So here the fundamental assumption that we make is that if this is an electron, and if a photon comes and collides with it, we are taking this to be an elastic collision so that no energy is wasted.
Right.
Like if this is the initial energy and this electron would start moving with kinetic energy K, and if this photon goes with a final energy, then we'll take it as K equal to EI minus EF. Which is the basic concept for an elastic collision.
Right.
If it would have been an inelastic collision, then there would have been some heat loss or anything which would have like resulted in some energy loss outside this equation.
Yes.
So here we neglect that fact and we take it to be an elastic collision.
Right.
So we have K equals to 3.4 into 10 to the power minus 18 joules by substituting
10
EI,
minus 6.6.
10 minus 6.6. EI and EF is like substitute and put in this equation, we get this value, which is the kinetic energy of the electron. So we write it as Ke.
Okay.
Next, we know the formula, like de Broglie wavelength for an electron would be given by h by root 2m k, where k is this we found ke.
So
H is the
basically,
Planck's constant.
so basically momentum is equal to root of 2 mke as
Yeah,
well.
we are using that fact.
Right.
Then you need to remember these values. I'll tell you again. 6.6 into 10 raised to the power minus 34, and this root over
2 into
m is the mass of the electron. You need to remember that as well,
Okay.
because it is also a constant and you are expected to remember. It is 9.1 into 10 raised to the power minus 31 kilograms.
Okay.
And then we put this value here, multiply by 3.4
Into 10 power minus
10 power
18.
minus 18, and then we get the value as 2.65 Armstrongs. That is 10 raised to the power minus 10 meters.
Armstrong is 10 raised to power 10.
Yeah.
Okay. So brilliant. Finally, we reached the lambda, which is the de Broglie wavelength. But one thing which we have to remember is obviously this formula, as per the definition of de Broglie wavelength. Also, the fact that there will be a certain number of constants whose values we have to remember. Something like Planck's constant, something like c, the speed of light, something like the mass of the electron, which is 9.1 in 10 power minus 31. So what we did here was we calculated the initial energy, which came out to be 10 into 10 power minus 18, final energy after collision, which came out to be 6.6 of the same, and then we use the normal fact that we are assuming that there are no heat losses or any other losses as such. So the kinetic energy would be the difference of the energies. So we found out that the kinetic energy is 3.4 in 10 power minus 18. Immediately when we knew that we can substitute it in this formula, where we knew h, we knew ke, we knew m, and 2 is a constant. So we finally substituted and the answer came out to be lambda is equal to 2.65 Armstrong. So this was question number 8. Right, so the 9th question says, photoelectric emission is observed from a metallic surface for frequencies nu1 and nu2, where nu1 is greater than nu2. If the maximum values of the kinetic energy of the photoelectrons emitted in the two cases are in the ratio 1:n, then find the threshold frequency of the metallic surface in terms of nu1, nu2, and n. So what is given here is that the maximum values of kinetic energy in two cases are in the ratio 1:n. So we do we take E1 by E2 is equal?
Yeah, we take that.
Uh-huh.
We have that E1 by E2 is given, the ratio is given,
Right.
and we're not given any numerical values,
True.
which leads to the problem being much simpler.
Exactly, because the answer is also asked in terms of variables.
It is asked in terms of the given variables. So this question can also be posed in a different way, where values would be assigned to the variables here, that is nu1, nu2, and n.
Right.
So that if we solve this problem, we can
Definitely
simply substitute in that, and then we'll get the values.
Okay.
So here what we need to do is we write Einstein's photoelectric equation for both the cases.
Right.
For E1 we get h nu1 minus nu naught, and for E2 we get h nu2 minus nu naught. So this is the Einstein's photoelectric equation, and you need to remember this because this is going to come in almost all of the questions of photoelectric effect.
Okay.
So we simply divide them, E2 by E1, which will give you nu2 minus nu naught
by nu1 minus nu naught.
nu1 minus nu naught. Here h gets cancelled because it is in both the E1 and E2.
So this ratio is equal to n, isn't it? Because E1 is to E2 is equal to 1 is to n.
Yeah, this is the ratio that is given. So you simply put it equals to n, and then it results in a simple equation here, this thing, which you can substitute, like simply simplify this, and then you'll reach the fact that nu naught equals to n nu 1 minus nu 2 divided by n minus 1, which is the required value of nu naught. So
Okay.
here it was fairly easy, but they might put different values for nu 1, nu 2, n, and then you need to like simply put those values before this place. Do not put the values in nu 1, nu 2 and n, because once you get this, only then it would be easy. Because if you put nu 1, nu 2 here itself, then you'll like make a real mess out of this problem, and then you'd feel like you're wasting a lot of time on this. So the thing is, always come to the last step where you need to substitute, and only then do the substitution.
Right. So come to the last step before substituting is one thing which we learned, and the other thing is, yeah, it was pretty simple. We just had to know the concept of Einstein's equation. So we came up with these two equations, which was pretty simple from what we derived from the question, and also we knew for a fact the ratio of their energies was 1:n. So we found out that this equation held true in this particular case. As soon as we did this, it was pretty simple for us to take the denominator on the left hand side, on the right hand side, multiply, take V naught common, and then finally get an expression for V naught in terms of nu naught, nu 1, nu 2 and n. Right? So this is pretty simple, but as we might say, this can be asked in the exams with different and complicated numbers. We should be patient enough to substitute it only at the last step where it is much simpler, right?
Yeah, only at the last step. Like as long as you can keep the variables and keep on simplifying, then try to do that.
Right.
And like put the values only when it is really required.
Right. Okay, brilliant. So this was question number 9 based on photoelectric emission.